We've learned about the frequency domain and the Fourier transform, and now we're going to use these frequency domain concepts to understand sampling in more detail. We'll start by talking about perfect sampling, which just means we're going to deal with this in a mathematical way. We assume infinite precision, and we're able to measure or sample functions exactly when we want and measure them perfectly. And we'll come back to think about errors later. So when you sample a signal, one way to look at it is that you're multiplying by a pulse train. So here's a train of pulses, and the pulse train is 0 everywhere except where the pulses are. So if we multiply them, essentially the pulses are selecting out individual samples of the signal. So it's sampling. In the picture at the bottom, the light gray sinusoid is just a reference to show you where the original function was. It's not part of the output. When you do this sampling, something very interesting happens in the frequency domain. The original spectrum, which I'm showing at the top, just as an example, is whatever that spectrum is, it is copied and shifted infinitely many times. And the spacing between the copies is, remember we're in the frequency domain, the spacing here is the frequency of the pulse train, which is the sample rate. So why are these things copied and shifted? Well, we've glossed over a lot of details. First of all, multiplication in the time domain is equivalent to convolution in the frequency domain. This is an amazing theorem. We just don't have time to go into detail and prove it, so you'll have to take my word for it. The second thing is when you transform a pulse train with the Fourier transform, you get a pulse train. And so convolution with a pulse train is what does the copying and shifting. There are more details about this in the readings, and if you really want to study this in detail, take a linear systems course, and you'll spend a lot more time with it and do things in greater depth. So let's talk about aliasing. Suppose I take a sinusoid and we sample it at these sample points, and the question is, do these samples uniquely determine the sinusoid? Well, that would be nice, but in fact, here's another sinusoid that goes through exactly the same sample points, but it's obviously a different frequency. Are there other aliases? Well, you can pretty much bet that if there are 2 of them, there's likely to be more, and I'll let you think about how to figure out what all the aliases are. Meanwhile, I have a little demonstration over here that illustrates aliasing actually happening. These are sine tones sampled at 16 kilohertz sample rate, and the frequencies are basically 1K, 3K, 5K, 7K, 9K, 11, 13, and 15. Okay, so let's play them and listen to what we hear. So isn't that interesting? As the frequencies of the sine tones are going up, what you hear is actually coming back down. So what you're hearing are aliases. So instead of hearing a 15 kilohertz tone, you're hearing 16 minus 15, which happens to be an alias. So let's look at aliasing in the frequency domain. Before we do the sampling, let's imagine that we have this spectrum. After we do the sampling, we shift and copy this spectrum, shifting by the sample rate, and we get something like this. Now, suppose that our original spectrum is not so narrow, it actually has higher frequency, so it looks like this. When we sample it, we're going to copy and shift it by the sample rate, but there's some overlap. Look at this. This is going to cause some problems. In fact, how do you get overlap? If the signal has components that are greater than half the sample rate, then when we shift it by the sample rate, part of that signal is going to overlap. Now, you might be wondering, why does this thing have positive and negative frequencies? And we're glossing over another detail here, but a negative frequency really is equivalent to a phase shift for sinusoids, and cosine is symmetric, so in the mathematics of all of this, the negative frequencies just naturally appear. So we have overlap here after we do sampling. So what sample rate should we use, and why does it matter? This was one of the key questions that we asked a couple of segments ago, and I added these little bells just to get your attention. Okay, you should think about this. We're now ready to answer this question. The frequency range, or the bandwidth, is determined by the sample rate, because we see that the higher the sample rate, the greater the shift in frequency, and the less likely we are to get aliasing. Oh, here's another answer. We asked earlier, how do we convert analog to and from digital? And I think we're ready to talk about that now. Sampling without aliasing is performed like this. We first take the signal and we pre-filter it to remove all the frequencies above half the sampling rate, which is called the Nyquist frequency. After we remove those frequencies that would otherwise alias, we put the signal into a sample and hold, and this takes a continuously time-varying signal like this and locks in the value of the signal for a short period of time. That's sampling and holding, and we do that at the sample rate. So we get this stair-step function, and during each of these quiet periods when the signal is not changing, we use an analog to digital converter to measure the voltage and output it as a digital signal. When we go to convert back to analog, we do almost the same thing in reverse. We first of all go from digital to analog, which produces kind of a messy, noisy signal because it takes a while for the analog conversion to settle down. So when the conversion settles down, we sample it and hold it. So that produces another stair-step signal like this. And we actually, to be honest, the perfect thing would be not to construct a stair-step, but to construct very narrow pulses. Sometimes conversion systems do something in between, narrow but not extremely narrow pulses. Anyway, this stair-steppy signal goes into what's called a reconstruction filter that removes all the high frequencies, which smooths it out, and we get the original signal back. So the reconstruction signal filter is removing all the frequencies above half the sample rate, again, the Nyquist frequency. All right, so here's a question. What does a sample mean? What do I mean by that? If I give you a single sample, or just let's say 3 samples, what signal does that imply? You might think, well, let's just linearly interpolate between those samples. That makes sense, but that's not quite right. You might think that each sample represents one of these sample hold pulses, but remember, that's not what the original signal looked like. The original signal is smooth and doesn't have these sharp corners. So you might think, well, there's some kind of interpolation going on, and maybe we smoothly interpolate, and that's more or less correct. The actual sort of meaning or implication of a single sample looks like this. It's actually a pretty big, complicated function. It's called a sinc function. It's mathematically sine of x divided by x, where x is the displacement from the sample, and x is 0 at the sample point. So, of course, that raises the problem, what's sine of 0 divided by 0? And in fact, there is an answer. If you take the limit of this, it's not unbounded. It actually, the limit is 1. And so that's, we define the point at the sample to be 1. And the thing sort of tails off like this. The sinc function goes through 0 at every other sample point, except for the one where the sample is, and there it's equal to 1. So isn't that interesting? The sinc function goes through 0 at every other sample point. So when you add these sinc functions together, if you're only looking at the sample points, the sinc functions only affect the sample that it's centered upon. And there, if there's another sample over here, you get a different sinc function to contribute that value. So when we have multiple samples together, you end up summing up these sinc functions, and the sum is going to go exactly through each one of these samples. It passes through each sample, and it produces a smooth output. And it's actually an infinite output. It tails off as 1 over x, but it never actually goes completely to 0. So why the sinc function? Well, an impulse has infinite bandwidth, and if you perfectly cut the bandwidth down to get half the sample rate, you get a sinc function. So when you reconstruct the signal, replacing the impulses with sinc functions, you get the entire continuous band-limited signal up to half the Nyquist rate. So samples are uniquely determined by the signal, and the signal is uniquely determined by the samples. So this makes this bijective, and I think that's really amazing. The fact that you can take a continuous signal, it exists at infinitely many points, but you assume that it has a finite bandwidth. You measure it only at discrete points, and you capture all of the information that's present in that continuous signal at infinitely many points. Amazing. So now we can answer, how can we interpolate samples to recover the sampled signal? Well, we just talked about it. We convolve with a sinc function. In other words, you form the superposition of sinc functions shifted by sample times and scaled by sample values. We add all of these up and we get perfect reconstruction. Unfortunately, this requires infinite look-ahead and infinite computation, but the sinc decays as 1 over time, so you can get very good approximations numerically on a computer without, it doesn't really have to be infinite to be pretty high precision.